Today we will study the Zeeman effect. We know atoms having nucleus and electrons revolve in its orbits. So, as orbital motion is there, spin motion is there, there will be orbital magnetic moment and also the spin magnetic moment. As electron is a charge, it revolves in this circular orbit. This phenomenon we know as a bound current. So, spin magnetic moment is also there and orbital magnetic moment is also there. Well, now these two these two magnetic moments, orbital magnetic moment and spin magnetic moment, interact with each other, and then if we apply that will be the total atoms magnetic moment. Okay, that's their summation. Okay, we can easily say. So they will interact with each other, and that resultant magnetic moment of that atom, that total magnetic moment. So that magnetic moment will be the atom's total magnetic moment. Okay. So that total magnetic moment, if we apply an external magnetic field, capital H. Okay. So we are applying external magnetic field to that atom. So those spectral lines will split. Why they split? Because the total magnetic moment of that atom interacts with this external magnetic field. Now, depending upon the strength of this external magnetic field, depending upon the strength, that will be, if it is weak, we call it Zeeman effect. If it is strong, then we will call it partial band effect. For our syllabus, we have only Zeeman effect, that is weak field effect. Okay. So external magnetic field H, the atom's total magnetic field, they are interacting. So we get the splitting of energy levels. Let's say energy level E. So that will be splitting of energy levels by amount B. So this causes due to the interaction between external magnetic field and total magnetic field of that atom. Now we have two types for Zeeman effect. First, normal Zeeman effect, normal, and second one is anomalous. Now we know Zeeman effect, a general normal Zeeman effect, has splitting of spectral line into components due to weak magnetic field. Okay, so that is normal Zeeman effect. But anomalous Zeeman effect, what is the difference between normal and anomalous? In normal Zeeman effect, we only consider the orbital motion of electrons. Okay, not the spin motion, because at that time when the scientists didn't know about the spin of electron, so they only considered the orbital motion of electron, calculated the spectral terms, observed the spectral lines. Okay, so they got the result normal Zeeman effect. But at some times when in the atom the spin is involved, they got something anomalous. Okay, anomaly or anomalous, what we call a phenomenon which is anomalous. Why we call it anomalous? Because we can't explain that phenomenon with present rules or present understanding, present knowledge. So at that time, the scientists didn't have any idea about the electron spin. So they got splitting of spectral lines in a more complex way. So they didn't understand this concept. So they just named it anomalous Zeeman effect. So whenever there is a spin and orbital motion, both are included, it is anomalous Zeeman effect, and without spin, it is only a normal Zeeman effect. So the spin without the spin, this is with the spin, this is a anomalous Zeeman effect. Okay, so this is about the difference between, this is main difference between normal and anomalous Zeeman effect. Both are in a weak magnetic field. If we use strong magnetic field, it will be a partial magnetic field. Okay, it will be partial magnetic field. Now we will study Zeeman effect in detail. Obviously, the anomalous Zeeman effect, because we know the spin now. Okay, So anomalous Zeeman effect here we will study this using vector atom model, which we are using already. So now consider this diagram here. So this is, it's called is spin angular momentum. Vector actually we are using. So this is S of an atom, that will be L, orbital angular momentum vector. We are representing vectors. So this is orbital angular momentum, spin angular momentum of that electron. So in Zeeman effect, they two interact with each other and precess along with their resultant J. We know this. Okay. So these two combine and precess about their resultant total angular momentum. Now, when we apply H, that is magnetic field, this whole system, this is H, this whole system precesses like this. This whole system precesses around the H. Now you can draw it here. This will be the precession like this. Okay. So this all combined total angular momentum. Now here we have spin angular momentum, orbital angular momentum, their resultant J, that is total angular momentum of that atom, of that electron. So that will, the total angular momentum will precess around the external applied magnetic field, that is H. Okay. So this is the concept. Now when we apply magnetic field, this is just a diagrammatical representation. Okay. Now when we apply H, what happens? We know this, that L, S and G. Here we have H. When we apply external magnetic field, we'll write capital G. Okay. Now when we apply external magnetic field H, what is happening? L and S interact with each other. They are precessing about their resultant J, and this J revolves around this H. Now this is in a weak magnetic field. Okay. Weak magnetic field, which is nothing but our Zeeman effect. But what happens when we apply strong magnetic field? The strong magnetic field, in strong magnetic field, what happens? The bond between L and S breaks down. Okay, so L is not interacting with S now, and the J obviously have no existence. We can say it is not relating now. So these two will independently interact, or these two will independently precess around this resultant J, because their bond is broken down now. Why? There is a strong magnetic field. In weak magnetic field, the bond is not broken between L and S. So their resultant, that is J, which will precess around this external weak magnetic field. Okay. So in strong magnetic field, the bond is broken because this external magnetic field is much higher than their bond. Okay. The interaction, the magnetic field between these two, the interaction between these two, so it is very high. So it will break down, and these two independent vectors will precess around this applied or external vector magnetic field. Now we will go to study weak magnetic field, which is from the syllabus. So when we apply H, weak magnetic field, to the atom, Zeeman effect will occur, anomalous Zeeman effect. Now when we apply this H to the atom, its energy E will change with small quantity, that is D. We have to calculate this D, that is interaction energy. Now so to calculate D, let's consider an electron charge E, mass M, velocity v in bored orbit with radius r. Okay. So this is electron moving in its orbit having charge E minus with mass m in a Bohr orbit of radius r. Now, we know electron is revolving in this orbit, circularly closed orbit. We call this bound current. Let's say I. I can be given as E by T, where E is a charge electron, T is a time period for the electron to complete its revolution. Okay, so E has value 2 pi R by V. So putting this value E V by 2 pi R. Now this is current, bound current. So the magnetic moment, now there is an electron moving in its orbit. So we know the magnetic moment UL will be current into the area enclosed by this loop. Okay, this total area. This area. So capital A, which is nothing but pi r square. Okay, so putting the value of I in this equation, we can write EV by 2 pi r is r square. So what we get EV r by 2. So this is the magnetic moment. Now, if we multiply here, multiply and divide with M, we will get mu L as E by 2M into LVR. Now here we can see LVR is nothing but this is momentum, this is radius, momentum, radius, this is mechanical moment or orbital angular momentum. Okay, so this is the mechanical moment of that electron. So we can write mu L is equal to E by 2M into PL. PL is nothing but mechanical moment. Okay. So this is value in classical mechanics. In this value, we are going to use quantum mechanical value. We know the value of PL, that is mechanical moment. In quantum mechanics, we have L h by 2 pi or L h cross. We know this quantity h cross. Okay. So that is mechanical moment. That is in classical physics. This is quantum mechanics. Okay. So okay. So we will use this value here. So we get mu is equal to E by 2M that value. So let's take this L outside and we 4 pi M. So that will be the magnetic moment, orbital magnetic moment of electron in this orbit. Okay? This is capital L. Now, so this is orbital magnetic moment of the electron. Similarly, we can calculate the spin magnetic moment of that electron. Here, mu s will be 2s EH by 4 pi m. So this is spin magnetic moment of that electron. So you can just add these two and write the final, the resultant mu j, that is total magnetic moment of that electron. Okay, we are considering balanced alkali metals, alkali atoms. So we are just considering single electron system. So whatever the magnetic moment will be this, that will be the total magnetic moment of that atom. Okay, we are just considering single electron in outer valence electron, valence shell of that atom. So whatever will be the magnetic moment, the total magnetic moment of that electron will be the total net magnetic moment of that atom. Okay.